So, you want to learn about AI. I do too. I mean, it seems incredibly complex. How does ChatGPT know how to repair the grouts in my shower at the click of my command, right? The argument I'm going to make is not that learning about AI is not complex. My argument is that it is understandable if you're willing to just put yourself out there, and I know that you are, which is why you can understand it. And today, long-windedly, I'm going to essentially teach you all of the intricate little parts, and I'm going to try and make it as conceptual as possible so that you might understand what goes on under the hood when you use an AI model. And from that, from some arguments that I'm going to make to you, we're going to decipher what AI really means, you know, what's going on, how can it figure out what kind of cat photos I like, and then, you know, the ball's in your court. You can really do whatever you want with this. If you know a little bit about computer programming, you can go and do this yourself and make your own sort of model, try and make it determine whatever you want. Put in some data. Data, let's start there. So, data looks like this. Data looks like this, where these inputs, what we call features, that's the terminology, and this output, a label. So, say we have an input. It could be a grayscale value. It could be a number, or it could be a picture, right? Say we have 3 features for some picture. We've got a cloud is the North Star and the moon, right? And our label is going to be beautiful nights. So I want to know, does this look like a beautiful night? Or is there just, you know, does it look like a not so savory night, some sort of a banal, maybe overcast clouds, whatever we've got. So, right, this is the logic we're going to have, where each of these features, these inputs, are going to give us an output, a binary value, right, of either true or false. It's a beautiful night sky or it's not. And we're going to build a model that can figure this out. And my argument to you is that we're going to go over some core math probability ideas that will give us the foundation for doing something like this. So, well, in this case, we really want to know the probability of seeing a beautiful night, given that we've got some values, some inputs, and some thetas. Why do we have thetas? Well, my argument to you is that this probability is going to look like the sigmoid function of theta transpose x. And this value looks like this. It looks like theta naught x naught plus theta 1 x1 plus theta 2 x2, and so on and so forth. And if you think about this conceptually, if I have a feature like the North Star, and I really think the North Star is super pretty, and if it's in a photo of a night sky, I might say that's a beautiful night sky. So then this theta value, this coefficient, we want to weight it a ton. That's going to go through the roof because we know that this input, this feature here, is the North Star. And we're going to figure out, using logistic regression, which is this main idea here, how to compute these thetas so that we can make our data look likely, right? We want our output to look likely given the data. So we're going to write this in terms of a PMF, and we're going to figure out the likelihood. We talk about likelihood equations and probability all the time, but we need something that's differentiable. We need something that's not so much a coin flip, because if you think about a coin flip, you might think about the Bernoulli, where you've got a PMF that looks like this, where you have your P, right, our probability, and then the complement of our probability, right? It's either it happens or it doesn't, right? It's 50-50 there's a dinosaur outside. There's either a dinosaur there or there's not. Not exactly, but we can see that this isn't going to work very well. Maybe I didn't stay in school for long enough, but this piecewise function, not super differentiable to me. I'd like to deal with something a little bit nicer looking. And if you think about it, the Bernoulli for one trial, right, one run through with some data to determine if this is a beautiful night sky, looks a lot like the binomial when you set your number of trials equal to 1. And we'll see that, say this was a binomial, our PMF for that would just be n choose k of p to the k times 1 minus p to the n minus k, right? What we see here is if n is equal to 1, k can either be 0 or 1, and we see that either term will drop, and we'll just be left with either the probability, if it's 1, that it happens, which is great, because we've got that, and then the probability it doesn't happen, the complement, if it doesn't happen, if k is equal to 0 with only one trial. And our combinatoric here, just n factorial over k factorial times n minus k factorial. Well, that's just going to be equal to 1 in either case. If you plug in 1 for n or 0 or 1 for k. We're going to see that works out nicely because if this goes away, we don't have to deal with it when we're differentiating. Again, I need to go back to school. I don't know how to do that, don't want to do that. It's not fun. So now that we have our PMF that we've picked and it's differentiable, let's get down to the nitty-gritty, figuring out our likelihood, right? We don't really want the probability that just this one feature makes the data look likely. Because what if I've got a nice moon, but I've got a ton of clouds in front of it, and they don't let the light through, they don't look super artsy, it just doesn't look great, it just looks like smog. So we really want the probability that we see all of the features, right? So our likelihood with respect to our thetas is just going to equal the product, right? It's probability with and. We want to multiply if we see some events, right? What's the probability I roll a 5 and then I roll a 6? Well, it's 1 over 6 times 1 over 6. There's a 1 in 36 chance I see that result. So I want the probability with and, so I have a product here. And then I want our PMF that we decided was the binomial when you set your number of trials, or your n, to 1. So this time 2y times 1 minus our probability. All to the 1 minus y. So then, again, you see this nice binary functionality where if your y is equal to 1, we get this term. If your y is equal to 0, we get this term. And that works out really nicely for us. The only thing that doesn't work out nicely for us is a product. Because, again, I don't know about you, but this doesn't look differentiable to me. That's going to be some huge chain rule if I pick a large value for n and yada yada. So let's put this in terms that we can better work with. The way to do that, right, is to really think about what we're going for here. Because really what we want is we want the arg max of theta. We want to set our theta values, as I said with that, think about the North Star theta coefficient, right? If I want a lot of North Star in my beautiful nights, then I'm going to set the North Star theta to a large value. So right, I want to set thetas to numbers, literally numbers, that will maximize our result here, will maximize our likelihood, right? I want to know the maximum likelihood, given the data, what is our result, right? Seems perfect. But we don't know how to differentiate this. It's all good, because we can take the log. Why can we do this? Well, the log is a monotone function. So that means it's either continuously increasing or continuously decreasing. In this case, right, it just is continuously increasing, but it's going to be a much smaller value. It's going to be a function that's much easier to work with. And we can make this, we can only take this step because that's true. Because the argmax of theta of the log of the likelihood is the same as the argmax of theta of the regular likelihood. It's just less work. So let's look at what that looks like. Remember, the log of the product is the sum of the logs, right? So we're going to say that equals the sum, I equals 1 to n of, let's take the log of this here. Funny functionality with our log is we can say we have, I'm actually going to write this up a little higher, and I'm going to go a little bit faster because I don't want to waste your guys' time, right? But if you think about how to take the log of this, log likelihood of theta, we have that. The log of the product is the sum of the logs. That's going to be an important rule to keep in mind, so we can push the log through the product, turn it into a sum. And look at this. We've done so much math. We've already taken out our product. That's great. So we can say with log rules, y, I, take the exponent, put it out front, of sigma theta transpose xi, right? That's our first term. And the log of the product is, again, the sum of the logs. Gotta quote Kelly, teaching me that. Great, love it. Gonna be stuck in my head forever. Whatever. But we got exponent, pull it out front, 1 minus yi times log of 1 minus sigma theta transpose x. Right? Look at this. We've already got a much simpler form that we can work with. We got the log likelihood. Now we're just going to try and figure out what the derivative is of this function here. Now think about why we want the derivative. Well, if we take some log likelihood, right, say that it's a degree 2 function. So we can easily plot it on a 2D plane. Well, that's never going to be the case, and with AI, right, it's important to remember there's this curse of dimensionality, because as I take a higher and higher order function, right, it gets increasingly complicated to visualize. Increasingly more complicated to visualize. In fact, you really can't. For a 5-degree, for a higher order polynomial with 6 dimensions, 6 features, right, we're going to have to think about the context of every result in the dimension of, given the dimension of each other feature. You're going to get a higher order embedding that it's just, you can't visualize it. You've got, if you've got 3 features, it's 3D. If you've got 2 features, it's 2D. But past that, I can't even tell you what it looks like. Nobody can tell you what it looks like. Don't believe them if they say they can tell you what it looks like. Tesseract, baloney. I don't like it. Forget it. So say we have some log likelihood value, right? If we take the derivative of this function and we try and optimize, remember, I think I remember that from calculus, not too sure, right? We can get some slope. And this will theoretically tell us a lot. It'll tell us, well, if it's negative, right, I want to reduce our value for theta. I want to subtract from our value to theta and plug in a new value here. Because now I can see that, we might have a new slope, and we're trying to maximize, the likelihood. So we got to optimize. Take the derivative, set it equal to 0, and then we got to figure out what steps and what direction we can take to turn this function by tweaking these thetas, these theta values. The only thing we can change, if I'm given a photo of a night sky, I can't take in or throw out north stars, right? We only want to change the things that we can change, our theta plugins, to figure out what makes this data the most likely. Okay, so let's do it, right? With large functions like this, with any number of terms. If it's a higher order, you want to take, if you have a bunch of different variables, you want to take the partial derivative of it. So let's take the partial derivative. Does anyone want to do this aside from me? Yeah, I don't really want to do it right now, but we're gonna do it because we're gonna take it with respect to any one theta, really, because we want to figure out how we can tweak each theta individually to make the data the most likely. Again, if you think about this in terms of minimizing loss, then you're taking the negative likelihood and you want to minimize that. Or you can just maximize the likelihood. But remember that calculus rules, the sum of the derivative of the sum is the sum of the derivatives. So we can push this through the sum, keep it out here. And, well, it might look challenging, and it does look challenging. It was challenging to myself, but once you know the answer, everything's easy. From there, we can just take, if we know we have theta j, we see this as, a function of what we're solving, we're taking the derivative in respect to, and this is just a coefficient. And we know derivative of log, or natural log in this case, very important distinction, yi, our coefficient, over whatever is within our log. So, right? This derivative of the log. Chain rule tells us we then take the derivative of whatever's inside the log. So I didn't tell you this about sigmoid, but I'll tell you it now because we're here, that it has a really nice derivative. It actually just looks like the function of the value times 1 minus the function of times the value, the function of the value, sorry. And that's really neat because we can just pull out the sigma by rewriting it like this. This is gonna be a lot of writing. But okay, we're almost done. Here comes the unintuitive part of all this. When you're taking the derivative, if you're like, Fields medalist derivative taker, you might think for 5 seconds about this step in the process. And we're differentiating with respect to some theta j, and we have this final part of the chain rule we've got to expand. So we need to take the derivative of theta transpose xi, right? Where we have a ton of x's, one of them being xj, one of them being theta j. If you think about it, you have, we'll start with theta 1, x1. You could really start with any value, right? Theta 0, x0. And then I'm going to say that somewhere within it is theta j, xj. Before we continue, just keep in mind, this is going to get us to an idea of understanding machine learning, right? All of this is all you got to know to make the building blocks of machine learning, right? I'm stuck, you're stuck, we're just going to push on through because this is what Chris calls like the boundary of knowledge, right? This is as far as people have got with this, or at least a good step of the way, right, at the boundary of knowledge. So if you can understand and learn something like this, you can then apply it and pretty much be right at the edge of what we as people understand, right? AI is new. AI is like, it's this wonderful technology, right? But we need to understand what makes it work so that we can, right? It looks incredibly complex, but if we learn this, if we push through, we can get to some truly remarkable results, right? That are worth knowing, that are worth putting the time in to learn. So we have some theta j. I digress. And we're taking a derivative with this huge sum. You can imagine there's just more values afterwards. Whatever, this linear combination of theta j's, xj's, and we have really only one coefficient on one term that we're differentiating in respect to. And if I remember from calculus class, from calculus correctly, you're just going to take this coefficient. Every other sum drops out, becomes 0. So that's the unintuitive part about it, that the derivative of this is just that one xj, right? Just the coefficient. That's it. That's the derivative of theta transpose x. And so we can move on. We can move forwards with that knowledge. Think about all of our thetas being features in an image. We want to figure out if it's going to be a beautiful night. That's what we're really doing, not all this hard math. So then, right, derivative of the sum is the sum of the derivatives. So we can just we can derive term by term, right? We remember our log derivative here, 1 minus yi over, 1 minus sigma theta transpose x I, right? Times derivative chain rule. We gotta do the inside again. Yeah, I know. Wait, we got negative theta transpose x times 1 minus theta transpose. My mistake. Let's put in 1 minus sigma of theta transpose x. I in here. Yeah, I. Make sure we got our subscripts right. And then what we said before, derivative, the final part of the chain rule, the inside term, is just going to be xj. Okay. Right. So now we have the partial derivative with respect to some theta j. And it looks pretty bad, right? But we can see some like terms in here, right? We've got a couple. Even xj, right? Doesn't look so bad. So pulling out these like terms, gathering them, we can see that we're left with we're still taking the partial derivative, the log likelihood with respect to theta j. Of times theta transpose x times 1 minus sigma of theta transpose x times xj. And then from here, we're left with this. Let me get it in here. yi over. Looks like, yeah, we got sigma of theta transpose xi. We're almost there. Minus 1 minus yi over 1 minus sigma of theta transpose x. Hopefully that's not too hard to see. All right, we pulled out our like terms. Now we have values in here, okay? We've got, it looks nicer, it's more compressed. How are we gonna work with it from here? From here, we're going to first figure out how we can subtract this fraction, because I don't know about you, I don't like subtracting fractions with denominators that aren't equal. I don't know how to add them, I don't know how to subtract them, but there's an easy way to fix this. We just multiply the missing multiple in each of the denominators by the numerator and the denominator in the other term to get fractions with the like denominator. So that's going to look like multiplying this side here by 1 minus sigma theta transpose x over 1 minus sigma theta transpose x. So we can rewrite the whole thing. Yep. And we will find they're mathematically similar to one another. Times 1 minus x all over All right. That's probably a little hard to see, but we can see with this term that we've now just brought this part of the denominator to the numerator and the denominator, and we can make that substitution without violating any mathematical rules. And this is going to be 1 minus yi times sigma of theta transpose xi all over sigma of theta transpose xi times 1 minus sigma theta transpose xi. All right, we're getting somewhere. We're getting somewhere. Now we can subtract these two, but I don't want to have a super large numerator with this operation here. So we're first going to just distribute within each numerator to make things subtract a little bit easier. We're going to say that was 1 minus, if you remember correct, 1 minus yi times sigma of theta transpose x. So we're going to say that's sigma of theta transpose x minus 1 minus theta times 1 This eraser's not helping. It's being so in the way. Theta transpose x. All right, let's move on. So we see that value for that numerator. Then we just distribute. We distribute the yi over here. We can see yi minus yi times 1 minus sigma of theta transpose x. Okay. Then, taking the denominator and the numerator, now we have them in terms that we can kind of appreciate. I know that this doesn't look great, but trust me, we're going to get it right. So, keeping in mind that this denominator is sigma theta transpose xi times 1 minus sigma theta transpose xi, we can then combine like terms in the numerator to get y minus sigma times theta transpose x all over sigma theta transpose x times 1 minus sigma theta transpose x. All right. So, if you're looking at this like I'm looking at this, it looks like we've got actually something that simplifies pretty nicely, because we've got a denominator here and a product here, so these terms just end up canceling, if I did that right. It looks like, yeah, so that cancels. This is good. And I wish I had some more space, had a better way of writing this, but, we'll persevere. And I appreciate you working with me. Your flexibility is always appreciated. So then we're left with this xj from our theta times times yi minus sigma theta transpose xi. How's that look? How's that look? Yeah? Yeah, this is it. So here we have our partial derivative with respect to theta j. And it looks rather nice. We've got the coefficient within our sum of thetas and x's, and our linear combination rather. And so this is going to pop out really nicely. But let's think about intuitively what this represents. So this is going to be our derivative that takes the slope of our likelihood function. What does the slope of a likelihood function represent? So say, we worked super hard to understand, we got finally here to this derivative. What it really means is our likelihood decreasing or increasing at the given theta? We want to increase the likelihood. We want to make our data, we want to make our parameters fit to the data as best we can. So we're going to increase the likelihood, increase the theta. So if this is a negative slope, right? Like I said earlier, we want to take away from theta. But, how much should we do it by? Typically it's understood. You would take the 1 to the negative times 10 to the negative 3, I believe. Anyways, so you want to take this, multiply it by your gradient. We'll see this in code later. But for now, it's just important to understand intuitively that if we have some function for the likelihood and we have its derivative, we can compute. We can use the power of a computer, take derivatives, and change thetas, and we can make our thetas change and fit the data to make it the most likely. And that's where the beauty of it is, because once you figure this out, then from there we can sort of encode our theta variables with, remember what I said about features? We can encode them with values. We can encode these thetas with values of really arbitrary numbers that we can't understand. ChatGPT has something crazy like 124 billion weights and biases. What they mean by that is ChatGPT has a heck ton of theta values, right? These weights that we have applied to our features here. And they've computed this. They've taken the gradient, they've taken steps to adjust their thetas and figured out when you give it a prompt, what makes that the most likely, right? Or based off of data they've already computed, what makes that data look the most likely given their model. So now that we've done this, let's go to see some examples of how we can make this work with a real world application, right? We've kind of rushed through this, but we know that we want to learn. We want to figure out how this all fits into some code. Let's go see it. So let's look at some code, right? So first things first, we had our sigmoid function. We defined it earlier. Here is what it is in code. I have it bounded by x values, or z values, sorry, for between the ranges negative 500 and 500, so that I can do some training without having my gradients sort of explode or die out with super small or super large values for this inside of my function. Now, we're going to import this data set called fashion MNIST. You might be wondering, what on earth is that? Why do I care? Well, for example, we're going to see that one of the sample images in fashion.mnist looks like a 28 by 28 grayscale image of pixels, rather, of various different pieces of clothing. In fact, there are a finite number of pieces of clothing. Here are some of different categories of pieces of clothing, right? But here are some examples. Here, this is a sandal represented as a 28 by 28 pixel image. Here's a shirt as well for reference. And my argument to you was that we could use this logistic regression idea to do some actual machine learning, to figure out, to tell and train a model, rather, how to tell the difference between these various different examples that we have of, and we'll actually see how many there are. There are 10 examples, each labeled 0 through 9. T-shirt, trouser, pullover, dress, coat, sandal, shirt, sneaker bag, ankle boot, right? All of these are different types of images that we could see. Now, right, this is just going to look like some bare bones code and formatting, but take my word for it that when I'm passing in an input, it looks like a 28 by 28 grid with each feature being a single pixel, and it'll have a grayscale value from 0 to 255 with representing the color that you see here, right? And we're going to pass in a ton of these. As you'll see, when we import this data, we're going to first split it into train and test data sets. And then we're going to basically squash each input down, because what we really want is a linear combination of thetas and inputs. We don't want to work with a 28 by 28 pixel image, right? This just makes vector multiplication and dot products so much easier to do. So we're going to reshape both the testing data and the training data. And then for our initial choice of thetas, honestly, because we've computed that gradient, it could really be anything. So we're going to make it a zero, a bunch of zeros in the shape of our vector, which is going to be actually a list of 784 theta values, right? But we're going to tune those so that each one of them encodes some intelligence per se, right? We'll see when we run it that we'll print out the shape of the data so that you can sort of visualize what it would look like. And for this, we're going to pick learning rate and number of iterations. These are, we'll find that with the learning rate, these are what's known as hyperparameters. So like your choice for these values can, when you vary it, will change how the model performs in training. So I found through training that with a very small learning rate, that the logistic regression model doesn't miss the mark when it comes to finding each gradient. It really will step shorter and shorter with smaller and smaller steps towards the maximum likelihood given the thetas. And I found that a good number of iterations to achieve this for each individual data set is equal to 1,100 iterations. The reason I picked this is just because I have a modulo function you'll see later. So when we want to do this, when we want to run this through our logistic regression model, right? You might think we've run into a problem here because we've got 10 different classes for type of objects in our images, right? We can have a sneaker or a trouser or a shirt or any of the other classes. So what we're gonna do, and this is what is so neat about what you've just learned, is that we can make individual logistic regression models to determine, right, if an image is an ankle boot or not, or if an image is a bag or not. So if I want to know if I want to know, I don't need to know if this is one of 10 different items. If I'm just one logistic regression model, all I care about is whether this is a pair of trousers or not. Okay, so then we're going to change, essentially what we're going to do here is change each training input, if it's an ankle boot, to 1, our outcome to 1, and if it's not an ankle boot, set it to 0. So that's what this code is doing here. We've got different training data for each logistic regression model where we want to train each model to recognize just one item, just one type of item. So here we go. Fashion MNIST. We're passing in our theta vector, our training data, our training labels, training features, training labels. We're going to pass in our learning rate and our number of iterations. And here's how we're going to do it. So we're going to look at loss and define these parameters prior, because if you make the best loss a very large number, then each concurring loss that's smaller and smaller than that number is the one we want to print to the user. So if I have a huge loss for the first calculation, it's not going to matter, right? Because we've initialized these variables well. And then when we think about our thetas here, we want to make a copy, because we don't really want to pass by reference our theta vector, because we don't want to change it each time. In fact, when we run this function, we want to calculate unique theta values for our function, for our parameter. So we want to calculate unique theta values that will be very good at recognizing shirts. And then we want to calculate unique theta values to be good at recognizing sneakers. Okay, so we're going to run through each iteration, and we're going to take a dot product of our training data with our thetas. This does essentially the linear combination for us. And then we're going to compute our prediction. Remember, squash that value down. And then our error is just going to be our feature result minus our prediction here. And then we are going to compute a gradient. This is just looking like the dot product of x and our error with divided by the length of y to normalize, right? Update our thetas. Remember, I told you we're going to apply our learning rate each time we want to add a step to our theta. So our theta is initially 0. Then after the first run through of the first iteration, we have some gradient, some step. It could be huge, right? Huge slope. Theta is going to go, straight up or straight down. And we want to only take a small step by adjusting the theta ever so slightly. So when we pass it back through, it's not going to be it's not going to be throwing our values out of loop. And here, we're going to compute our loss each time to determine how we're doing, how the function is doing. Here, we're going to print it out to the user. And this, if you notice, we're going to print it out every 100 iterations so that we don't, lose our minds with how much compute is going down. Actually, when I calculated the original theta values, my computer basically turned into a jet plane because of some of the compute. Just needed to bring wet paper towels from the bathroom to basically towel off my MacBook as it was burning up, and I feared for the worst. But we also have this additive. This I added because if we look at a logistic regression function and we're calculating thetas, we'll notice that at a certain point, we stop really improving a heck ton, and we see that we sort of plateau and we kind of find the right theta values. So if that becomes the case and we don't improve by, if we improve by less than this much, then we want to stop early. This is called early stopping. This helps with some of the compute so that your MacBook doesn't explode. And then finally, we're going to print out that we've updated the theta values after running through 1,100 iterations of gradients and gradient ascent, essentially. And we're going to return our best theta. Notice that we've calculated best theta with our best loss. So we have our loss minimized in this case or our likelihood maximized, and we have our best thetas picked. And this is going to happen each time individually. And then after we run this function, we can say we have a vector of thetas here. Our theta vector is then equal to this function times one copy of our zeros times our training data times our specific y result times our learning rate and our number of iterations. Notice how we have specific results here. Our training data is always going to be the same. We're always going to have the same number of images. The same, in this case, you'll see there's 60,000 different images. And each time we run it through a different function. These are all commented out because running this takes up just a lot of compute on my computer. So each time I run it, I don't want to have to, worry about them overriding some of my np.saves. See, we save our results for our thetas because that's our intelligence, right? We've trained the model. We want to save all of our digit values, our float values for all of our thetas so that we can keep the intelligence, keep the model, and I digress, right? So if I want to train a model to recognize address, I need to know whether it's address or not. So that's why each label input varies, but the training data is always the same. So then after all this runs, which takes about 10 to 20 minutes, we'll see that we have encoded all of these over here. And you can't read them, but it's just because it's in a format that's not super supported. We can't really take a look into what we have here, but we can imply that these thetas, whatever inside this file is essentially just all the theta values that we calculated represented in binary. So like if I want to know if I've got a coat, if I'm looking at an image of a coat, or if I want to look at an image of a trouser, right? It's just going to be a ton of 784 different binary values that will give us our inputs for our model here. And then from there, once you've saved all of that, it's pretty simple to just go through and essentially load all of our values and run our function, use theta knowledge down here on all of our different thetas here with our testing data and our training data. And this is the big reveal, right? Here we've put all of our models to the test. We've essentially, what we've created on the board, we've recreated here 10 separate times. We have 10 different linear regressions, and let's go through how exactly we use each 10. This is, again, a lot of the same sort of implementation, but we have some probability with the dot product here, and then we squash it down and we append it to a prediction here, right? And then so given our functions, our thetas, 784 different thetas are going to weight a linear combination, and then we're going to squash it down using the sigmoid. And remember what we said about the sigmoid. It makes our value really, really small, easy to comprehend. And when we do that, we'll see that larger values get squashed slightly less. So the biggest value from each of these different computes here, each of these different predictions, is what we output, right? We append all of these predictions, so right to this array predictions, to this list, in each index. So if it's a t-shirt, index 0, we have a probability that it's a t-shirt, and that's the genius of it here. By taking a binary classification and recognizing that we've got probabilities here, plugging them into this list as predictions, and from there it's very simple. We just figure out what our biggest prediction is, and we return it. And then we also do some work to compute confidence, which it's not super challenging. It's just the biggest probability from the class. So if my function ran and it had the probability of predicting a t-shirt, it would essentially just store that probability and return it, the max probability. And that's going to be our confidence score. And we obviously run through to figure out what our best is, starting at -1, which is a value we can't have. So we're going to initialize it to some low value, and then it's going to iterate each time, getting larger, figuring out which one it's going to be. Okay, final prediction is just going to equal these two things. And then from there, we're going to compute some accuracy, and we're going to print out a nice example, a nice visual here of the first 10 samples. So essentially, while I can't really show you this because it's not really compatible with a printout, I can show you what the first 10 samples were from this data set that we have up here called fashion MNIST. This is sort of very similar to digit MNIST. It's just a different application of a categorical. So after we do all that, we're running this function, predictions and confidence, use state and knowledge. And this is just some work I did for other stuff, but ignore that. That's not important. It's commented out. It's essentially, for all purposes, the same thing we're doing up there. It's just a much smaller data set where you can sort of really easily, intuitively understand what each of your inputs do to your theta. And now when we run this function, we'll see. We don't need rainbow.csv. We will run this function, and it will crash because TensorFlow is not working. That's horrible. Oh no, we're good. Okay. All right. So as you can see, we have our true label, right? Our first 10 images for their true label, and then our model's predicted label, and then its confidence here in this final column. We can see that it actually works. It did it pretty well. In fact, 100 accuracy here, predicting which image contained which piece of clothing. And this is all done through 10 different encoded sort of intelligences that the model has. And then we compare them sort of in a categorical fashion. And this is very, as an aside, this is not how you'd really want to implement like a machine learning algorithm. This is very bare bones, step-by-step blocky code where something like PyTorch really simplifies this out and makes things a lot easier. But this is it, guys. This is everything that we just learned. And let me show you directly where each application was from our math. We see fashion MNIST. Each time we compute a gradient, we take the dot product of the error, and there we're using we're literally using the derivative that we computed earlier. So it's all that it takes, and it will predict, and you can train your first machine learning neural network, so to speak, with only one layer. Call it the input and output layer neural network. And yeah. Hope you found this informative.